Till now, we know what is the capacity of frequency flat deterministic MIMO channel and we know how to compute it. We know MIMO gives you R parallel seesaw links and capacity is given by log 2 1 plus Es by mt and naught lambda I. Capacity of an orthogonal MIMO channel is m times the capacity of seesaw channels. That means when you have orthogonal, you can write capacity as m log 2 1 plus Es by n naught. And when CSI information is available at the transmitter, we utilize water filling algorithm that computes the amount of power that would be associated to each mode of transmissions. In that case, we simply multiply here with gamma I, where gamma I indicates you the power that is allocated to the ith mode. Then we have also studied the capacity for SIMO, which is given by C is equal to log 2 1 plus Es by n naught Frobenius norm of H. And we also looked into capacity of MISO. When there is CSI, in that case the capacity is equivalent to this one, and when there is no CSI, then capacity is equal to the capacity of seesaw channel. And we have also seen capacity of MIMO with random channel, and we concluded that if we have m spatially wide random channel and as m grows very large, we have linear increase in capacity. So that means in that case we have C is equal to m log 2 1 plus Es by n naught. So till this part we have already covered. Now let us look at transmitting symbols in MIMO when there is no CSI available at the transmitter side. So we have received signal y is equal to square root of Es by mt h times s, where s is a symbol vector, s1 so on up to smt, and then we have noise. If h is orthogonal, so when h is orthogonal, what you can do, you can simply multiply received signal y with h Hermitian. When you multiply, you will have h Hermitian h, which is equal to identity because h is orthogonal, and this can be replaced with another form n tilde. And what is this s? So what you will get, s is s1 to smt. So when you try to write down yi tilde, which is equal to square root of es by mt si plus n tilde. So what you can see from here is that there is no influence of other symbols. That means we have one-dimensional pipeline. And there is no influence of other symbols, and we have interference-free channels. Case 2, when H is not orthogonal, but H inverse exists. In that case, what we can do, we can apply zero forcing mechanism, which simply says that you have the received signal, you multiply the received signal with H inverse. So when you multiply, you will get S plus H inverse N. Again, we can represent this part with N hat, and S is nothing but a symbol vector. So again, from here also we can see we do not have any influence of other symbol on the current symbol. Now if H is non-square, then also we can recover the symbol S by using this particular form. That means we have H Hermitian H inverse times H Hermitian. And again what we will see, we will get the similar kind of form. So as a result, we can apply different approaches to recover symbols. Thereby, we are having parallel transmissions. Now, when we have CSIT at transmitter, we get lambda i's of the channel, and based on the lambda i's, we allocate power. Let's say gamma I. So the block diagram could be seen as follows. We have the transmitter, then we have receiver. At the receiver, we are doing perfect estimation, and we are sending ideal feedback to the transmitter. So that transmitter, what it can do, it can first do pre-coding. that means V. And at the receiver side, what we can do, we can basically combine the signal with U Hermitian. So we have multiple antennas here and we have multiple antennas here. Okay, so the receive signal equation, we know it can be written as root y is equal to root es by mt into h into s tilde plus n. Why s tilde? Because we are not directly sending the symbol s. Instead, what we are doing, we are sending v times s. So this is what we are sending. So we can replace s tilde with vs. So we have written here vs. And now h can be decomposed using eigenvalue decomposition. Sorry, so using singular value decomposition. So we get u d v Hermitian. And at the receiver side, since we are doing combining, at the receiver side, what we can do, we can simply multiply received signal with u Hermitian. So you get u Hermitian y, which is equal to you multiply u Hermitian here, and then with the noise you multiply u Hermitian. Again, this will be just noise, so we can write it simply n. V times V Hermitian would be equal to identity. U times U Hermitian would be equal to identity. What is D? D is a diagonal matrix that contains the singular values of H. So we can simply write sigma I times Si plus N. And here also what we can see, we do not have interference and we can establish parallel links between transmitter and receiver. So for both the cases, whether we have CSI or we do not have CSI, it provides us with the parallel links. And this gives us the gain of spatial multiplexing. So we are transmitting S1 to SMT, S1 to SMT in parallel, and there is multiplexing, and this multiplexing is in space domain. Hence we call it as spatial multiplexing. And because of the feedback, we have precoding. In this particular method, we are doing precoding because we have feedback, and this method is known as SVD based precoding. Okay, and number of parallel links would be equal to what is the rank of H, and the spatial multiplexing is gain is basically equal to how many number of parallel links you can create. This number of parallel links that you can create. Now let us look at what is the impact of spatial correlation. What is the influence of spatial correlation? And we know from our previous slides, we have studied that H can be represented as RR raised to power half, HW RT raised to power half. HW is the spatial white matrix. RR captures the correlation at the receiver side, and RT captures the correlation at the transmitter side. Then they are normalized with unit power, and we assume expectation of mod Hij square is equal to 1. And also we assume that Mt is equal to Mr is equal to M. And from our capacity expression, typical capacity expression of MIMO channel, we know capacity is given by log 2 determinant of I Mr plus Es by Mt and not Hh Hermitian. Since Mr is equal to M, we can basically simply write I of M. So now next step what we can do, we know what is the value of H from here. We can substitute this value of H here. So what we will get, we get C is equal to log 2 determinant of Im plus Es by M and nod. You have R half, you have HW, then RT half. Now since we have Hermitian sign here, so we will write RT half, then you have HW and you have RR half. So this is what we will get. So what is this? This is simply RT. At high SNR basically means Es by N naught is greater than 1. In that particular case, what we can do, we can simply write capacity as log2 determinant of Es by n naught HW Hermitian plus log2 determinant of RR plus log2 determinant of RT. And both of these terms, the effect is same, so one of the correlation can be studied. If R is orthogonal, that means not correlated. If R is orthogonal, they are not correlated, then this term would be equal to 0 and this term would be equal to 0. Now, if there is some correlation, then this both terms, they will have negative impact on the capacity. Both the terms will be negative. It will have a negative effect and the capacity would be decrease. So if R is orthogonal, then these two is equal to 0. Otherwise, there will be negative effect and the capacity will decrease. Now let us try to conclude what we have studied. So when we have MR and empty number of antennas at the receiver and the transmitter, what to use them for? So we can use them to achieve spatial diversity gain. We can use them to achieve spatial multiplexing. Okay, when we have MT and MR, we can use them for diversity, we can use them for receiver diversity, transmit diversity, we can use them for multiplexing. Open loop, that means you directly send the symbols. Closed loop SVD means there is some precoding done before sending the signal. Or what you can do, you can achieve some diversity and some multiplexing, there would be some trade-off. We have seen when you have low SNR conditions, then capacity is dominated by the square Frobenius norm. In case of high SNR, capacity is dominated by lambda k. And when you have parallel links, when you have spatial parallel links, in that case, capacity is always equal to m times log 2 1 plus Es by n naught. Now let us look at both spatial diversity and spatial multiplexing side by side. So we know this particular plot, we have seen this already many times. This is probability of error versus SNR in dB. So plot is like this. So as you keep on increasing the number of antennas, you basically shift the curve towards the left hand side. So as we increase the diversity order, we move towards the AWGN channel. So means diversity order, let's say this is diversity order M. So as you increase this diversity order, you move towards the AWGN channel. And now when we are talking about low SNR scenarios, low SNR scenarios, that means at this particular region at low SNR, our probability of error would already be high. And in case of spatial multiplexing, what we are doing, when there is no CSIT, we have parallel links. Okay, we have parallel links. When there is no CSIT, what we are doing, we are putting the power Es by m lambda I to each of the branches. And when there is CSIT, what we are doing, we are using Es by m lambda I gamma I off. So each of these link will experience low SNR, then CISO channel, and we will have high probability of error for each of this link. And probably this will not be a good idea to go for the spatial multiplexing at low SNR. Instead, what we can use, since we are at low SNR, we can utilize this for spatial multiplexing, and we might have the chances to lower down the probability of error. So at low SNR, spatial diversity is preferred. Why spatial diversity is preferred? Because probability of error at this particular region is already high. Okay, so when you divide it into multiple pipelines, each of these pipelines will experience low SNR region, and in low SNR probability of error will be already high. So it would better to go with spatial diversity. So that means in low SNR region, you can utilize multiple antennas for array gain and diversity gain. In case of high SNR, the pipelines, You can employ spatial multiplexing. You can allocate power to each of these pipelines, and even if one of the pipeline has a higher probability of error, what you can do, you can discard these pipelines, and you can use these pipelines for spatial multiplexing and rest of the antennas for diversity. For example, if you have, let's say, m number of antennas, total number of antennas are m at both transmitter and receiver, and you have r number of parallel links. Now, out of r, one has higher probability of error. So what you can do? You can discard that one. So you will get, let's say, p parallel branches now, and the rest of the antennas, that means m minus p antennas, you can utilize them for spatial diversity. So what you can do, at high SNR, we can employ both spatial diversity and spatial multiplexing simultaneously.